So the second talk of the morning, Masanori Hanada will tell us about Monte Carlo approaches to superstring theories for dummies.
Yeah, so now screen is bridged, but maybe later if we get another adapter, it will become normal color. And yeah, I was told that the numeric Monte Carlo simulation, lattice supersymmetry should be Greek to almost all the audience and give a very elementary introduction. So at least for first two talk, I will try to be very elementary. And firstly, let me introduce motivation. So I want to use gauge gravity duality to learn about the string or M theory, because the duality claims that super mu theory can work as a definition of a quantum gravitational system. And for that purpose, we want to solve this side. Okay? And in principle, physics is very easy. So we just have to define the theory and diagonalize the Hamiltonian or perform path integral. And the problem is Hamiltonian is very big. Physicists are just spending 100 years for diagonalizing Hamiltonian, and it's still very hard. And the question is how to do it practically. And this time, I take this approach, path integral, and use a numerical method, such as lattice, very similar to lattice QCD simulation, to do this task numerically. And one of the goals of this talk, using the numerical method, is a numerical solution of the so-called three-quarter problem. And before going to technical detail, let's first let me try to give you a big picture what I want to solve. And this is the problem. So in gauge gravity duality, the basic conjecture is, of course, gauge theory and gravity should be the same. If we calculate the same thing in both sides, we should get the same result. And that in late 90s, people calculate the energy density in four-dimensional n equals to 4. Maybe it was free energy. Maybe it was free energy, but anyway, basically it's the same. So they plotted it as a function of temperature. So for each given temperature, they plotted it as a function of the Hooft coupling lambda. And many gauge theories can be considered, but people first studied for the n equals to maximally n equals to for maximally supersymmetric convenience. And then recoupling, of course, we can do perturbative calculation in Yamil theory side. And they got some number times n squared times t to the fourth. N squared and t to the fourth just follows from the Hooft counting and dimensional counting, and this constant is not trivial part. And assuming that duality is correct, people could do the same calculation at the strong coupling by using weak coupling gravity dual. And they got something like the same number times 3/4. And 3/4 is close to 1, so people thought it's a good start. And people try to say how things change if we change coupling slightly. So take into account some effect of lambda perturbatively, then it went down slightly. And people try to take into account the 1 over lambda correction here by looking at the stringy correction in gravity side, and it went up a little bit. So they actually seems to be connected. That's very good. But what is going on here? Can we really see if they are smoothly interpolated as people expect, or if maybe if we just calculate very precisely without relying on gravity dual directly mu theory, can we really reproduce this result? It's an unsolved problem. And sorry, so this is just what I said. Lambda expansion gives this pattern, alpha prime expansion makes a curve upward. And we want to study this region, which is not accessible by perturbative calculation in Yang mu side by using numerical method. Okay, so already here I said it's a good start. But that assumes duality is correct. And the duality is not proven. So if we can directly calculate this number from YAMU theory, of course it's a very good support for the duality. And at the same time, we can also study this parameter region where weakly coupled YAMU's method, the weakly coupled gravity method cannot tell us anything. So numerical method can be powerful for this purpose. And here I took the example of 4D n equal to 4. But of course, there are many other examples of gauge gravity duality proposal. And if you look at the paper by Itsaki, Marata-Sena, Zuneshain, and Yankinovich, which appeared right after Marata-Sena's first paper, they consider maximally supersymmetric MLs in lower dimensions, p plus 1, and this p can be 3, like in usual ADS 5 shifty correspondence, or 2, 1, or 0. And p plus 1 dimensional theory should be dual to black p brane. And p equal to 3 case is the same as ADS 5 processor. Original ADS shifty correspondence is p equal to 3 case, but they claim that smaller p is also fine. And numerically, p equal to 0 is easiest, and we can do actually very precise test. And the reason that p equal to 0 or smaller p is easy is very apparent. So if you imagine you approximate three-dimensional space by using lattice, if volume becomes bigger, you need a lot of points. But if you have only 2 dimension, 1 dimension, or even less dimension, you just need less points. In p equals to 0, this is not even field theory. It's just a metric quantum mechanics, and you only have time direction, and you just have to discretize time direction. But if you have a 3-dimensional space, you also have to discretize space dimension as well. So if you have 10 points for each direction, then for p equals to 3, you need 10 to the 4 points. But for p equals to 0, you only need 10 points. So simulation is much cheaper. Okay, this is the reason smaller p is good. But at the same time, as a quantum gravitational system, they are equally non-trivial. So there is no disadvantage that we study smaller p. But we have advantage that numerically it's easier. And this is the model. So Lagrangian is, detail is not important at this moment. But this is just a dimensional reduction of 4D n equals to 4, or equivalent retained dimension n equals to 1 supermills to 0 plus 1 dimension. So this is Lagrangian. So we have a time direction, but this is Lagrangian. So this just depends on time, and there is no space. Okay, and there are 9 bosonic matrices, x1 to x9, and 16 Grassmann odd field, and both are in by n matrices. And for near to Hooft limit, this theory is conjectured to be dual to type 2A black zero brane near to Hooft limit. And very big difference from 3-dimensional theory is that Hooft coupling, which is defined by multiplying n to this Yam's coupling to Yam's square, has mass dimension too. Because action is do not have dimension, and the Lagrangian has dimension of mass. And in 3 plus 1 dimensional theory, this part carries mass to the 4th. And in 4 that case, we have a 3-dimensional integral here. Then that cancels 3 of the dimensions, and without assigning the mass dimension to GM mills, we can get the right dimension. But this is 1-dimensional theory. So in order to compensate dimension 4 here, this GM square must have dimension 3. And this coupling set the scale, energy scale of the system. If you know lambda QCD in QCD, it's analogous to lambda QCD. Okay, any energy scale should be measured by using this unit. And when we set the fifth limit, lambda is fixed, and t is fixed, and the energy should scale like n squared. For equivalently, because this is just a length scale, we can fix lambda equals to 1. For equivalently, we measure temperature by multiplying this factor to make the combination dimensionless, and fix this combination to 0, and fix this dimensionless energy to be n squared. They are the same thing. And the interesting thing is strong coupling and low temperature are the same. Because when t is small, or lambda equals to large, this combination becomes smaller anyways. Okay. So very big difference from a four-dimensional case is temperature or energy scale and coupling, strength of coupling are related. Anyways, modulo that difference, this Mandelstam and company suggested the good gravity dual of this theory. And by calculating black hole mass in dual gravity side, if the derivative is correct, then we can calculate energy in gauge theory side. And below, I use this dimensionless unit, and I set lambda equals to 1. So when I say t or e, it secretly means this combination. But because of this, strange combination, because coupling constant has mass dimension, actually naive power counting doesn't work. And very strange power can actually appear. If you calculate energy divided by n squared, it's something like 7.4 times t to the 14 over 5 plus some unknown constant, which can in principle be calculable, but people don't know from string theory side, times t to the 23 over 5 plus unknown constant times t to the 29 over 5 plus da da da. And this corresponds to supergravity, this corresponds to alpha prime cube, this corresponds to alpha prime fifth, and so on. And we also have Pollard string correction. This is string theory correction at strong coupling. And as I said, strong coupling is...
This is the low temperature function.
Yes, strong coupling is low temperature. And at low temperature, if the duality is correct, then energy, or strictly speaking, dimensionless combination, this dimensionless combination, as a function of this dimensionless temperature, should approach this curve, 7.4 times t to the 14 over 5. And the deviation should be like this.
So can you understand these powers in terms of irrelevant deformations around your...
In field theory side, I don't know. In field theory side, I don't know. In gravity side, it's just alpha prime expansion.
So in principle, you know how to reinstate the appropriate powers of the coupling.
So from field theory side, I don't think it's possible.
I guess what I'm asking is, can you calculate this 14 over 5 as connected to the dimension of some irrelevant operator?
Don't think so, because of this, because of the fact that lambda has dimension. Argument is very complicated.
No, but that's fine, because this irrelevant operator, because it's irrelevant, it has a dimensionful coupling, which is going to be related to lambda. But then it has a scaling dimension, and when you combine these two informations, it should give you the 14 over 5.
The quick answer I can give you is nobody has succeeded there, at least. Maybe the fact it's quantum mechanics makes this situation very complicated. Anyways, as you say, the low temperature is strong coupling. Okay, so we should see supergravity plus a small string correction. And the high temperature is weak coupling, and there we can do weak coupling calculation, and we can easily show that this should scale like 6 times t. And so at weak coupling, gauge theory should agree with this straight line, and at strong coupling, it should agree with this strange curve. And how they are connected. This is the zero-plane version of three-quarter problem, and the essence is exactly the same. And there are some simulations. For example, we started it in 2007, and this is a 6 times t, and this dotted line is a class high temperature limit plus some small perturbative correction, and that we coupling our simulation result actually agree very well with this curve. And after strong coupling, it seems it's going closer to this line, supergravity line. And Cotterell and Wiseman also in 2008 tried similar calculation. And here I have shown E, but in their case they studied E divided by T. So high temperature region, this is 6 times T, become constant 6 in their case. And they could also see that at the high temperature, the simulation result go close to this constant, and at the strong coupling it starts to deviate and seems to go close to this curve.
So wait, what computation are you doing here exactly?
So explaining that is the goal of this lecture, but what we did was we did Monte Carlo simulation in matrix model side. So we numerically calculated it. And in this talk I will explain how to do it numerically. And here I'm just showing the result. Okay, to understand how to make such plot is the goal of this talk.
Will you explain it before the third lecture?
Because you are leaving tomorrow?
Yes.
Okay. And this is a result from 2016. So this is a zoom up of low temperature region. And this is a supergravity result. And this is our simulation result. And these two curves are previous fit of previous work. But we could see that the simulation result could be fit very well by using t to the 14 over 5, and t to the 23 over 5, and t to the 29 over 5. And if we, for example, use 3 parameters to fit this data, fixing this power, for example, we can actually get 7.4. We can actually reproduce a result of supergravity. And if we change this power to something else, actually we cannot really fit the data clearly. So in that sense, this result strongly suggests that alpha prime fraction is also reproduced correctly by gauge theory.
I think that you fit using 3 parameters. I thought that so you had this B and this C, right? And these were the only 2 parameters in your low temperature.
Yeah. In string theory side, of course. But in string theory, we can calculate this 7.4. But the problem is whether we can reproduce that value from gauge theory. And actually, we can. And I will also show that how much we can constrain these powers. But that's some lecture, very sorry for you. Anyways, so I hope this plot can give you the flavor that such numerical method can be powerful. And I want to explain how to get it. And first, I explain how to perform Euclidean path integral by using very simple example. And also, I will explain how to define super-Mu theory in the form we can actually simulate it by using Monte Carlo method. And then I will show how to get those plots by combining these two. Okay, so before talking about the Monte Carlo, why do we need it? Why not the other method? And for that, I should show the one way to get to disaster. So imagine we want to integrate the p variable function, f of x1 to xp. So we have some curve. And imagine we try to approximate integral just by summing the area of these bits. This is what we have learned in high school or college. And by taking the limit when this beam is very narrow, we can define the integral, right? This is the definition of Riemann integral. And imagine we take n beams for each variables. Then if we have 100 beam for 10 variables, 10 variables is actually very small. Typically we need 1,000 of variables in order to do such calculation. Okay, but imagine it's 10. Then actually we have to sum n to the p times, which is 10 to the 20 in this case. And if we take, we have 15 variables, it's 10 to the 30. And this is a huge number. For example, imagine we use a supercomputer in my collaborator's lab, which used to be the fastest one in the world, which is called Riverboat of Sequoia. And it's a 20 petaflops, which can do 2 times 10 to the 16 double precision floating point arithmetic every second. It's a huge number. It's huge. It just occupies one big building. And imagine we can do, we just have to repeat the calculation 10 to the 20 times, 10 to the 30 times. This is an unrealistic assumption because usually you need more than one calculation for evaluating each term. Okay? But even if we take the most optimistic scenario that we just need one manipulation for estimating each term, we need this much. And it takes 5,000 seconds for this, and 634 years for this case. So just 15 variables, 100 pin for each, takes more than 600,000 years. And I tried to see, the meaning of this number. And first I thought, okay, at that time probably all human beings were in Africa, but actually that's not precise, and Homo sapiens wasn't there, wasn't in the world at that time. It seems Homo erectus or something were walking around this region, but it takes that long just to calibrate this small integral. Okay, so this is just a disaster. So we need some smart method, or stay very healthy to live very long. Okay? So that's the reason Monte Carlo method is useful. So name Monte Carlo comes from Monte Carlo, which is a casino area in Mona or somewhere. It's a very expensive resort, which usually physicists cannot go. And this is a picture of John von Neumann. He made up this name, I think. So he had the idea of using a random number to do this kind of calculation. And random number and gambling have something in common, so he named it like that. Anyway, Monte Carlo. So this is the kind of calculation we want to do. Okay? So consider field theory on Euclidean spacetime. The reason why we consider Euclidean rather than Minkowski will become clear later. Okay? And imagine we have an action S on phi, and the phi is just a scalar field or something. And by Monte Carlo method, what we can do if we do everything right, in the following the rule I explained in following slide, is that we can make a generate configuration of field phi with a probability proportional to exponential minus s. Okay, then expectation value of a certain operator is defined by this. Okay, so we multiply observable and exponential minus s and do path integral, and then divide it by partial function. But if we have such algorithm, then if we have n samples following this probability distribution, and if we send n to infinity, then we can approximate this path integral by this average. Okay. And here I said this is a probability distribution. So of course, probability must be real and positive. And so if, as long as exponential minus s, this path integral weight is positive, the method I explained from now can be applied. And in Minkowski space, actually we need the weight exponential is. This is complex. And still people are trying to apply Monte Carlo for such situation as well. But it's become very tricky, so I don't explain such a situation this time. That's the reason why I concentrate on Euclidean signature. And the basic idea is generate a chain of configuration. C0, C1, C2, da da da. And this C is a set of this field phi. Okay. So if you have a lattice, on each lattice side, value of field phi is defined. So this C0, C1 are set of values of phi at each point. And we change field configuration gradually with some probability, some transition probability. And the choice of that transition probability is very crucial. And I will explain how to choose such transition probability. And if we take this transition probability right, and if this chain of configuration are Markov chain, which means the transition probability from CK to CK plus 1 does not depend on previous history, then in the long run, we get the probability distribution, WK, which is proportional to this way. There's some mathematical theorem. And that mathematical theorem has some assumptions, and we cook up this chain so that it satisfies that assumption. And there are many algorithms to cook up such chain. And the simplest one is Metropolis algorithm. And for super mills or QCD, we use a more sophisticated one called the hybrid Monte Carlo or rational hybrid Monte Carlo. But all the essence is in Metropolis. So in this talk, I explain only Metropolis.
Are all the Monte Carlo depends on Markov chain or the?
Not necessarily. So in some sense, what I'm talking to here is Markov chain Monte Carlo. And so typically, if you use random number, it's Monte Carlo, I think. I don't know if there's a precise definition for that, but typically people say if you are playing some random number, it's Monte Carlo. Original example by von Neumann is not Markov chain Monte Carlo. He just used random number.
Can you already elaborate the physical, the intuition for the Markov chain, the Markov processor? Or is it really?
I don't know if your system is exposed to noise and the noise is time dependent, then it should be something like Markov chain.
Excuse me, why do you want to specifically do this Markov chain Monte Carlo, not just I don't know?
In other method never work for this complicated problem. Maybe some other method can also work, but the Markov chain Monte Carlo, we know that it's very useful.
I don't know why. I would explain.
I will explain it can actually work, and of course I cannot explain other method can never work.
No, for instance, if I take some field configuration and then evaluate the variable.
Okay. Just one configuration.
Yeah.
But then it's not path integral, right?
Then I generate lots of configuration.
Yeah. But if you do that without having this probability weight, you can never.
No, I generate field configuration, evaluate action, and then
good.
and sum with some probability.
I will give you the notion of importance something like that.
Something like
Okay. If you just randomly generate configurations, almost all configuration has this very small weight, like e to the minus 10,000, which never contribute to path integral. So you need a lot of samples. And in Markov chain Monte Carlo, we can generate only important samples, which really contribute to path integral. And that's a difference from that disaster. And this is a paper proposed by Metropolis, Rosenbluth, Teller, last Teller is that famous Edward Teller. Father of hydrogen bomb or something. And I had that, this is called Metropolis algorithm because he's the first author and other people's name are hard to pronounce. And Also, I have that actually the guy who actually invented this algorithm is one of Rosen brothers. But so the lesson we can learn from here is it's good to hire a good boss. It's important to hire a good boss. Then your name can remain in history. Okay, so I will explain this Metropolis algorithm here. And if you understand the Metropolis algorithm, basically you understand all Markov Chain Monte Carlo. Others are just technical improvement. So there are several basic requirements. Markov chain, irreducibility, aperiodicity, detail balance. Let me explain these 4 conditions one by one. So Markov chain means that the transition probability from one configuration to the next configuration does not depend on previous history. Okay? And if you take, just for simplicity, just consider the case of one variable integral. Okay, we have just one variable. Xk means, so you have a chain of x's, and xk just means value at k step. And from xk, we have to make xk plus 1, okay, by slightly changing xk. And imagine we add some random number, which is chosen from this range, and take the delta x to the uniform random number. It's perfectly fine. Because this process does not refer to previous history. But if you take this dx to be in this range, for example, by using xk minus 1, it's not Markov chain because it refers to the past. And imagine xk minus 1 by coincidence becomes 0. It just stuck there. And so you never get the reasonable chain of random configuration. So there are, of course, many other reasons that the Markov chain property is needed, but this is one example which illuminates that why Markov chain is important. Okay. Otherwise, so depending on detail of previous configuration, it can stuck in some wrong place. And irreducibility means any 2 configurations in path integral are connected by finitely many steps. For example, if you have 2 islands in a parameter space, the 2 islands of x, and imagine they are separated by distance L, and if your step size C is smaller than L, once you start with this configuration, you can never move to this configuration. So irreducibility is not satisfied here. But if the step size is bigger, then so if you just take data, so I said step size, but by step size I just mean this C. So step size can be between 0 and C, right? So I just set x to be x plus smaller number. Smaller number is shown from here. Then sometimes from this configuration you just get very nearby configuration. Sometimes it can just jump to this island, and you can go to any configuration by finitely many steps. And this condition, importance of this condition is very clear, because if you cannot reach some part of parameter space, then of course you cannot estimate integral. Okay, it's very clear. Aperiodicity is a bit more tricky, and I cannot really explain why this is needed in a simple manner. But anyway, statement itself is very simple. Period of C means greatest common divisor of a possible number of steps from some configuration C to itself. Okay, so in this example, for example, delta x can be 0. I just said it's a uniform random number in this region. So if delta x is 0, the next step is just itself. And if delta x is non-zero, once she goes to something else, but in the next step it may come back. After 2 steps it may come back. And it can, so from starting with configuration C, you can come back to the original configuration with any steps. So greatest common divisor is just 1 in that case. And aperiodic means period is 1 for any C, any configuration. And for example, if you take a very pathological example like this, xk is always positive for even k and always negative for odd k. Then period has to be even, at least 2. So it's not periodic. It's not aperiodic. So such a updating algorithm, updating is not really good. You cannot get the right number. And you can do make such pathological example. For example, by multiplying, taking xk plus 1 to be xk times some negative random number. If you do such thing, you never get the right result. And the most important thing is detailed balance condition, which means, so this exponential minus s is the weight you want to generate. Okay? And the transition from probability from C to C prime times exponential minus s of C has to be the same as transition probability from C prime to C times exponential minus s C prime. This is detailed balance condition. And the reason why it's needed is intuitively simple. Mathematical proof is more complicated, but intuitively very simple. Okay, so imagine after a long time, this chain converges to some stationary distribution. And then, if you just go one step further, the distribution should be the same. You just shift, one step. Okay, so that means this stationarity condition should be satisfied. However, if this condition, detailed balance condition, is also satisfied, then we can calculate this stationary distribution very simple, in a simple manner like this. So exponential. So we can show that exponential minus s of c satisfies this constraint, because condition, stationarity condition, because this is by detailed balance condition. You can flip c and c prime, and then you can take this sum with respect to c, only this part, because c prime know nothing about c, and the sum of probability from c prime to c means the probability of c prime goes to something, but of course the c prime goes to something. So probability, if you take some with respect to c here, this is just 1. So you get the exponential minus s c prime. So this weight satisfies this stationarity condition. So stationary distribution should be this, which is the thing we want. And basically, satisfying other conditions are rather easy. You just have to be carefully satisfy the balance condition when you cook up the algorithm. And if we do the simple example of a Gaussian integral, probably you can do any complicated simulation. You can even do super-Mills lattice QCD as soon as you understand the Gaussian integral. So we take action to be x squared over 2. We just have one variable and perform this Gaussian integral. Of course, we know how to do it analytically. But every time I forget if it was square root of pi over 2, so I look at Wikipedia, but I think you can do it. And let's see how Metropolis algorithm works for this case. So we can change the field, which is just variable x this time, randomly. And this random variation can be chosen from this range between -1/2 and 1/2. As I will explain, you can change it to be -1 to 1, or -0.1 to 0.1. And if you change the range, actually the efficiency changes. But for simplicity, let's take it to be 1/2. And then, so we try to vary it randomly. However, we accept the change with this probability. Here, delta S is the difference of the action. So if action becomes smaller, delta S is negative, exponential minus delta S is bigger than 1. So you always accept this change when action decreases. But when action increases, you accept only with this probability. You don't always accept it. So if action doesn't change much, you accept it with a high probability, big probability. And if you action did increase a lot, you don't accept it. This is Metropolis algorithm. And the detailed balance condition can be seen very easily. So without loss of generality, let's call this x plus dx to be x prime. And without loss of generality, we can assume that delta s is positive. Then, transition probability from x to x prime is 0 if difference of x and x prime is bigger than 0.5 by definition. And 0 equals to 0. So for them, of course, if difference is big, the detailed balance condition is automatically satisfied, equal to 0 equals to 0. Okay. And if our difference is smaller than 0.5, what happens? Then, so here we assume that the delta x is positive. So acceptance ratio, acceptance probability for this change is exponential minus delta s. But acceptance probability for transition from x prime to x is 1. Because we say the acceptance probability is this. And then exponential minus s of x times p to the x prime is proportional to exponential minus s times this probability, which is exponential minus s x prime. And exponential minus s x prime times this transition probability is proportional to this times 1, which is exponential minus x prime, and they are the same. So the detailed balance condition is almost trivially satisfied. And other conditions are also satisfied. You can check it. Periodicity, reducibility, and the Markov chain. So if you generate x this way, you get this. So here I just started with x equal to 0 and use this algorithm to get the chain of values of x. And starting with x, it fluctuates around 0. And if you see the distribution of these values, with 100 samples, you get this. And this is a Gaussian distribution, and it's not very close. But if you have 1,000 samples, the situation is getting better. And if you have a lot of samples, actually, you can see it converging to actual Gaussian distribution. So you can really make a distribution, path integral weight, by using this algorithm.
Well, the reason you get this Gaussian is because you use Gaussian action, or it's because of central limits?
Because we use Gaussian action. If you use more complicated action, you get the more complicated distribution. And for example, if you plot how x squared changes, then it fluctuates like this. It of course takes just a positive value. And expectation value has to be 1. And actually, if you just take the average of these numbers, it changes like this. It starts around here and just fluctuate, converges to 1. And if you take average of x itself, for example, yeah, it starts from 0, it fluctuates around here, but eventually it converges to 0. Convergence is actually a bit slow here. And in a lattice gate theory, typically we just repeat the same thing by using a higher dimensional version of the integral. And if we start with x equals to 10, what happens? It will answer to your question, important sample. So at first, so x starts from 10, but of course, exponential minus 10 squared over 2 is exponential minus 50. This is very small way. So such configuration is not really important, right? What you can see is x comes close to 0 very immediately, very fast. In close to 0, x close to 0 actually contribute to the integral. Okay? And it start to fluctuate around there, 0. And what we can see is such rare configuration which do not really contribute to path integral do not really appear. So if you start with such configuration, chain just converges to go close to important configuration and just fluctuate around there. And then we can just remove this part and estimate the expectation value using this configuration. Then we get the right answer. And the point here is after this summarization process, only important sampling, important configuration appear. Configuration with small weight never appears once we reach summarization. So we can effectively sample only important samples. That's the reason why we don't need really many bits like a usual Riemannian integral. So we can do calculation within reasonable time. And the program is very simple. This is a C program for Gaussian integral. So here, I just define a bunch of variables and set x to be 0. And n accept just count how many times update is accepted. So always we try to change the value of x randomly, but we do so-called Metropolis test, which I explained before. And so it's not always accepted. So we should better measure acceptance rate as well. And this is the main part. So I just keep the value of x as backup x, and then value of the actual before randomly changing x is just calculated here. It's 0.5 times x times x, and generate random change dx, and shift x, and calculate action, and just generate random number between 0 and 1, and say if exponential minus delta x is greater than that random number, we just accept it. Otherwise, send x back to the previous value so that x doesn't change. So this is a so-called Metropolis test. And in other much efficient algorithms like HMC or RHMC, what we do is we just improve this updating process. Other part doesn't change. And maybe looking at the bad example will make you better understand the situation. What happens? We do Metropolis test as usual, but take this dx from here, between -1/2 and 1. What happens? So there are 4 requirements: Markov chain, reducibility, aperiodicity, needed balance, and which condition is broken. Actually, detailed balance condition is broken because this allows us to go from 0 to 1, but 1 to 0 is forbidden. Then if you go back to the check of a few slides back and see how we check the detailed balance condition, you can see that detailed balance condition is not satisfied here. Then, if we use this stupid wrong algorithm, this is the distribution we get. So here, this is actual Gaussian distribution, but this is the distribution we get. So here, we have some bias to send x to larger value. So distribution shift to positive side. And we don't get right answer. So that's how we can understand the importance of those conditions. And also, yeah, I said, okay, then I said in other algorithm we just improve the updating process. But still, even in a Metropolis algorithm, we can improve the efficiency. And free parameter here is C, which describes how big change is allowed. And you can imagine that if C is very small, then delta S is almost 0. So change is almost always accepted. So in a sense, it's very efficient. However, it's just change is so small, it's essentially random walk. So though acceptance ratio is very high, so the configuration is updated every time, change is too small. In that sense, it's not efficient. If C is too large, once change is accepted, configuration changes a lot. So in that sense, it's very efficient. But because delta S can become really large, actually update change is all very rarely accepted. So in that sense, it's not efficient. So you can easily see that acceptance rate scales like 1/C. And if xk and xk plus n are too small, the change is too small, they are not really independent, right? If difference is order 1, we can roughly call them to be independent samples. And we should see how efficiently we can make independent samples. So we have to figure out how many steps are needed for configuration to forget about past. Okay, and then if C is large, once change is accepted, then change is already big, so just n equals to 1 is the answer. When C is small, it's almost random walk. So the change, the typical change is C square root n, and it has to become as large as 1. So n has to be 1/C squared. You need many steps. Okay, and by multiplying the acceptance, by dividing it with acceptance rate, we can show that we can see that for big C, we need order C steps for getting one independent sample. For small c, we need order 1/C squared step to get independent sample. And there is some sweet spot in between. And if you can actually make plot by changing value of c, in this case you can see that c equals to 4 seems to be optimal. And I think I only have 10 minutes or something, 5-10 minutes.
7 minutes.
7 minutes. Okay, let's try to explain a bit more, but if I run out of time, I can just postpone only to tomorrow. And so far we have learned how to calculate VEF, okay? Absolute expectation value of x or x squared. And I didn't explain how to calculate partition function. How can we do it? Okay, so we want to calculate the partition function z, which is integral of exponential minus x. And suppose you know partition function for simpler action, like Gaussian integral. we can do it actually by hand. Then, actually, we can, by using Monte Carlo method, we can calculate this ratio. And we can multiply normal analytic value to get z. And how to calculate this ratio? It's very simple. So by definition, z over z0 is integral of exponential minus s divided by z0. But exponential minus s can be written as a product of exponential minus s0 times exponential s0 minus s. That means by using this weight, we have to calculate expectation value of exponential of s0 minus s. This is how we calculate partial function. However, this in principle work always, but there is a so-called overlap problem. For example, imagine we have a function x minus c squared over 2. And we chose s0 to be s of x at x0. So take s0 to be x squared over 2, but take s to be x minus 100 squared over 2. Then importance sampling, because we are doing importance sampling, we sample only these configurations, but the actual distribution we want is here, right? And there's almost no overlap. And we almost always sample these configurations, but this weight is very small. It's exponential minus 5,000. And every once in a while, so every exponential 5,000 times, we pick up this configuration, and it gives huge weight, and it dominates path integral. And clearly, importance sampling is not really working here. However, if we define sk to be x minus k squared over 2, then exponential minus sk and exponential minus sk plus 1 have a big enough overlap. So we can calculate this ratio, and then we can just take products. This way, we can estimate any complicated integral just by using Monte Carlo. And this is already good enough to numerically integrate, for example, so-called ABGM matrix model. ABGM matrix model describes partial function of the ABGM theory on 3 spheres. And this is just a matrix integral obtained by applying supersymmetric localization to ABGM theory. And there are many beautiful analytic results, but we wanted to study it numerically to understand some subtleties. And there are 2 parameters, n and k, which correspond to size of gauge group and the chance angle level. And what we have to do is this integral. We just have to calculate this integral, then this is the partial function. And what we have to do is very simple. We can just use Metropolis. Actually, we used a bit more fancier algorithm, but basically Monte Carlo. And we can calculate this ratio very easily. And if K1 and K2 are sufficiently close, then overlap is sufficiently big, and we can easily calculate this ratio. And by calculating this ratio for various K1 and K2, we can get to this G. And this is how you can numerically do such complicated integral. And and this is a comparison of numerical result and exact result for n equals to 2 case. And one thing I'm very proud about that is we did a numerical calculation, and we found the Marigno's miscalculation. So Monte Carlo is powerful enough to find a very tiny miscalculation in the analytic calculation. Anyways, and I'm running out of time, so probably about sign problem I can explain tomorrow. So then I should stop here.
Questions?
So in condensed matter, the Monte Carlo method is known to be less accurate than other methods. So I'm just interested in on that particular graph, the comparison of results. What's the
so
just like as a match, right? What's the allowed error margin then?
Error bar is almost we cannot really see. It's very tiny.
Yeah.
It's like less than 0.1%, if I remember correctly. But here, so you say the Monte Carlo is less accurate. In the sense, so here I used applied it for complicated integral, but the number of variables is not very large. And also we can estimate, calculate, and that because of that, simulation is much easier. We could create tons of samples. But if you try to study bigger system, like I will explain SuperML's case later, then cost for generating one configuration is very big. And you cannot really make many configurations. Like by using supercomputer, you can generate only 5 samples every day. Then, of course, precision goes down. And if you have some other powerful method applicable, that can be more efficient. But at the same time, Monte Carlo can be applied to rather generate problem. That's advantage.
Other questions?
For the so for fermionic model, you probably have a finite number of filter space, and you can in that case you can directly diagonalize Hamilton. Maybe it's big, but for the 1D case, so compared to the Monte Carlo, which one is more efficient?
But even in that case, Hilbert space grows exponentially. Okay, so for example, even bosonic system, of course, we have into many excitations, but we can truncate it and we can diagonalize it. Some people are trying it, but the problem is in the case of fermion, with so n fermion system, Hilbert space is 2 to the n, and if you try to diagonalize it, calculation cost exponentially increases. And if you can apply Monte Carlo method to such system, avoiding sign problem, which I explain tomorrow, the cost typically grows with some power over.
Okay.
Yeah, that's the advantage.
I think for super young meals, right, I mean, you have many matrices, fermionic matrices. So each matrix is n times n. So each matrix is like 2 to the n squared for the dimension. But you have like 9, right? Well, no. How many fermionic matrices do you have?
9 matrices, each has n squared components,
Yeah.
so 9n squared.
So it's 2 to the power 9n squared.
Yeah,
So already n equal 2 is probably the limit, more or less, what you can do. So you'll never be able to do large n by direct diagonalization, unfortunately, for the interesting models. If you had only one matrix, yes. But for the interesting models, it doesn't work. No.
Well, when you count the number of samples, you have independent.
Yes.
What is this independent?
Okay, so point here is in this method, you change x little by little. So if you look at this configuration and this configuration here, apparently there is correlation. Or even a simpler case is this. So you start with x equals to 10. Then it takes for a while to come down to 0. And why here you get big values like 4 or 6? Because it's correlated to initial condition. So there it takes for a while for two configurations to be uncorrelated. Because we just gradually refresh the value. we don't completely refresh the value every time. We just change it slightly, little by little. In that sense, they are correlated, and they are not independent.
Yeah, but how do you measure the correlation? You use this action or something like
Okay. Of course, there are many statistical methods to do that. And here, I just very naively say if values are very different, that would mean you have to go through very complicated change, so they should be independent. But of course, in this Gaussian case, it's really easy to see. But in higher dimensional example, you cannot really draw a picture, so such simple statement cannot be made, and you need some bootstrap method to estimate the correlation. And there are many methods. For example, the so-called jackknife method is very easy.
No, my question is, if you in order to evaluate the correlation, you need action, or it's just statistical?
Statistical, you don't have to know the action.
Okay.
And here, strictly speaking, I say 1 because I knew that given this specific action, if difference is order 1, they should be uncorrelated. It's kind of cheating because I knew that the typical range for x integration integral domain for x is order 1.
Okay, let's thank Masanori again. We'll start again in 5 minutes while we set up.